ever really thought about what holds you together? I mean, what really keeps you from just falling apart? Today, we're going to take a journey, starting with the big picture of our bodies and zooming all the way down to the cellular level to look at our most essential lining. Think of it like a smart, living wallpaper. Let's get into it. So here's our game plan for peeling back these layers. First up, we'll see where this epithelium stuff fits into the 4 basic fabrics that make up our bodies. Then, we'll zoom right in on its main job as our protective inner shield. After that, we'll get into the nitty-gritty of how these cells are engineered to stick together so incredibly tight. Then we'll take a tour of all the different kinds of linings and what they do. And finally, we'll tie it all together and see why this tiny cellular world is a huge deal for your health. All right, first stop, the body's 4 fabrics. You can think of your body as this incredibly complex building, but what's amazing is that it's all built from just 4 basic types of material, or tissue. So let's figure out where our star player, the epithelium, fits into this grand blueprint. Okay, check out this table. It lays out the 4 core fabrics of the body. Now, just focus on that top row, the epithelial tissue. The real secret is in that column called extracellular matrix. See how it says small amount? That's everything. Unlike, say, connective tissue, which has tons of filler between the cells, epithelial cells are packed together, shoulder to shoulder, super tight. And that's what lets them form the perfect, continuous barriers we're talking about. They're the ultimate gatekeepers of the body. So, let's build on that idea. We're now focusing right on that boundary tissue, your protective inner shield. This is where we get to the real heart of what epithelium is. It's the essential barrier that lines pretty much every single surface of your body, both on the outside and, you guessed it, on the inside too. So let's get a nice, crisp definition up. You see it right there. Continuous sheets of cells. The 2 key words to remember are sheet and barrier. Don't think of it like a random pile of bricks. It's more like a perfectly built, seamless wall. And this wall is incredibly smart. It acts like a very selective bouncer, deciding exactly what gets in, what stays out, and what it needs to kick out. And you know what? This bouncer is a serious multitasker. Its most obvious job, protection. Your skin is the perfect example. It's literally shielding you from the world. But it also handles absorption. The lining of your intestines, that's all epithelium, designed to soak up every last nutrient from your food. And finally, secretion. You know the cells in your glands that make things like sweat or hormones? Yep, that's epithelium too. It's a real workhorse. Okay, this is where things get really, really cool. Epithelium has some characteristics that are kind of paradoxical. First, it's avascular. That means it has 0 blood vessels running through it. You know when you get a tiny paper cut that only skims the very top layer of skin and doesn't bleed? That's why. But, and here's the crazy part, it's innervated, which means it's packed with nerve endings. So you don't bleed, but you definitely feel it. And here's the real kicker, its superpower. It has an incredibly high capacity for regeneration. It's constantly getting damaged and constantly rebuilding itself. It's a shield that's always being repaired. So, if these cells create such a powerful barrier, how in the world do they stick together so well? That brings us right to our next section, the amazing engineering of this living wall. We're about to look at the microscopic nuts and bolts, or maybe cellular superglue is a better way to put it, that holds this whole thing together so perfectly. Now, this diagram shows a super important concept called cell polarity. It sounds complicated, but it just means that every single epithelial cell has a distinct top, a bottom, and sides. See the very top of the cell, facing the open space? That's the apical surface. Now look at the very bottom, where it anchors down. That's the basal surface, its foundation. And the sides, where it connects to its neighbors, those are the lateral surfaces. This strict organization is absolutely crucial for the whole sheet to work as a proper one-way barrier. Okay, so let's get a closer look at that cellular superglue. This table breaks down the entire toolkit. Right at the top, you've got tight junctions. Think of these like the Ziploc on a plastic bag. They create a waterproof seal so nothing leaks between the cells. Just below that, adherence junctions act like a belt, cinching all the cells together and giving the sheet strength. For even more heavy-duty connections, you have desmosomes. These are like industrial-strength spot welds, holding on tight when a tissue gets pulled or stretched. And finally, gap junctions are fascinating. They're tiny little tunnels, creating a direct communication line from one cell to the next. Every connection has its own very specific, very important job. All right, now that we know how these walls are built, let's go on a little visual tour. In this section, we're going to see that not all epithelium looks the same. And this is a perfect showcase of one of the most fundamental rules in all of biology. Form always follows function. The shape of the cell is perfectly matched to the job it needs to do. First up, simple squamous epithelium. Just look at how incredibly thin and flat these cells are, almost like flat paving stones. The drawing on the left shows the basic shape, and that image on the right, that's what they look like in the tiny air sacs of your lungs. So why this shape? It's all about speed. Oxygen needs to get into your blood as fast as possible, and the super thin, streamlined design is the perfect way to make that happen. Okay, next up, let's look at simple cuboidal epithelium. And as you can probably guess from the name, these cells are shaped like little cubes. Here you can see them lining a duct inside the pancreas. This cube shape gives the cell way more internal volume, more room for all the little machines it needs to do its main jobs, which are secretion and absorption. So for a cell that has to work like a tiny factory, the cube shape is just perfect. And then you have this absolute marvel of biological engineering, transitional epithelium. This diagram shows it in two different states. Up top, it's relaxed, and the cells are all plump and piled up. But on the bottom, it's stretched out, and the cells have flattened and slid past each other. Now, where would you possibly need a tissue that can do that? In your urinary bladder, of course. This is what allows it to stretch and fill up, and then shrink right back down to size without ever springing a leak. It's a truly amazing, dynamic lining. All right, we've made it to our final section. We've been deep in the weeds of the microscopic world, so let's zoom all the way back out and ask the big question. Why does any of this actually matter? This is where we connect all this fundamental biology to the real world, to our health, and to modern medicine. And this right here is the critical takeaway. When this perfectly engineered system starts to break down, the results can be devastating. For example, if those belt junctions we talked about fail, cancer cells can literally unstick themselves from the wall and spread throughout the body. If the immune system mistakenly attacks the spot weld junctions in your skin, that wall loses its integrity, causing painful blistering. And if those Ziploc seals in the brain don't work right, well, that can compromise the vital blood-brain barrier. Every single one of these tiny connections is absolutely essential for keeping us healthy. So let's end with this thought. This tissue, the epithelium, is our body's first line of defense. It's our direct interface with the outside world. It is constantly taking a beating, and yet it is constantly, silently, tirelessly repairing and regenerating itself. So what does this invisible, nonstop work tell us about what it really means to be healthy? Maybe it suggests that health isn't some static, unchanging state, but a dynamic, resilient, and continuous process of protection and repair. Definitely something worth thinking about.